Gotta love it. Ah, where is that? Where's that? What is that? What is that? Okay, sure. Right, though. Let's start this up. Let's go. Let's go. I believe in us. I don't believe in me, though. Can I? Actually, you know what? I probably shouldn't have done that. That shows that I have pirated The Lord of the Rings. That's not a good thing. Uh-huh. I'm now black. Blacked out. That was not what I wanted to say. Apologies. Right. I should have put this all up before the stream. That would have been much nicer. However, as we can all recognize, I am an idiot. Ah, there we go, there we go. Here we are again. Back at it. This goes up. There we go. Right, we were not in this location. We were much farther down. Right, did we go through this? I think we did we not? Yes, we did. Holy sheesh, we got two different things left, and then there's the end of the experiment. What's the end of the experiment, honestly? Oh, just thank you note. That's nice. Right. While I play around with this, I'm just going to check audio. It would be quite embarrassing if Twitch had no audio. Ah, there we go. What about the YouTube? Hey, yeah, she got a good shit. Good shit. Right. Right. I was what's going on? Okay. I don't think we can hear my air conditioner, which is directly next to me, which is a good thing. Good thing. I should still turn it off, should I? Eh, okay. I've returned. Okay, this is the last section of matching. Looks like a fairly long one. Good stuff. I'm glad because getting into the advanced features, unsafe rust is going to be harsh, I assume. That sounds like the really advanced stuff. Advanced tree to advanced types, advanced functions, and closures. As well as macros. I'm glad that we do that. I'm curious how long that is while I just dally around. Ah, that's fairly short, comparably. Right. I'm going to start at this point. Okay, so we got pattern syntax. In this section, we gather all the syntax valid in patterns and discuss why and when you might want to choose one. Matching literals. As you saw in Chapter 6, you can match patterns against literals directly. The following code gives you some examples. We have let x equals 1. We match against x with 1, 2, 3, and anything else. Not very useful. This code prints 1 because the value of x is 1. This syntax is useful when you want your code to take an action if it gets a particular concrete value. Okay, yeah, usually this would be from either user input or from some settings piece. I would assume. Like, it's not like you're gonna put this just directly in your code, unless you're using some weird magic number. Well, magic number is an entirely different thing. Unless this is some sort of constant that you're using that a person can change in the source code. Perhaps this is telling you whether or not it is on a specific platform, specifically OS X, or if it's Linux, or horrifically, if it is Windows. Match named variables. Named variables are irrefutable patterns that match any value, and we've used them many times in this book. However, there are complications when you use named variables in match expressions. Because match starts a new scope, variables declared as part of a pattern inside the match expression will shadow those with the same name outside of the match construct, as is the case with all variables. In listing 1811, we declare a variable named x with a value of sum5, and a variable y with a value of 10, and then create a match expression on the value x. Look at the patterns in the match arms and print line at the end, and try to figure out what the code will print before running this code or reading further. So yeah, we have x and y, which is sum 5 and 10. Right on match x, if the value is sum... Have we already done this? Huh. Did it take me this long to recognize that we've probably already done this? No, this is... I don't think we have already done this. This is just seemingly repetitive. Whatever it is. Did we not do this last week? Huh. Right? Sum 50, which fails. It got 50. I am certain that we've done this. Let's walk through what happens when the match expression runs. Right, the issue here is that y is shadowed, and that is what it previously stated. Yeah, we've already done this, haven't we? Okay, I guess I'm gonna go to my previous session. Right? 2 weeks ago, 2 months ago. Ooh. Live. Right. What did we do last week? Where did we end up? I feel fairly embarrassed. I got that far down without recognizing I think we've already done this. If this would load, we could see, but it won't. Huh. Oh yeah, I forgot. YouTube won't load for me, so I have to use a proxy. This is so strange. I legitimately cannot use the main YouTube. I have to use some proxy in order for it to work. I don't understand why. It's probably because I'm on a VPN, but I'm not going to not use a VPN for that. Right, we ended up at... where? 18.3. 18.3. Yeah, we actually did finish this entire thing. Oh, so we're going into a quiz without... Okay. Must have been a reason I stopped. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. That's where we left off. Right, so we got x, which is a tuple of 0 and 1, matching against x if it is a tuple of anything, and the variable y, anything unused, and the variable y. This matches, because it is anything, and we have the variable y, which takes in whatever is here. If y is equal to 0, nope, it doesn't match, because this second, the right-hand side, does not match on the if statement. 0 and underscore, we print b. This does compile, and it prints b. Obviously. Right. Consider the following program. We have an array, or sorry, no we don't. We have a vector holding a tuple with 0 and 1. Let question mark? Which of the following are valid patterns that could replace the double question mark placeholder? Right. I don't think that's a valid piece. I believe this is a valid piece. I don't believe this is a valid piece. In this section is an identifier. This is an expression. That, perhaps? I believe this will actually work now that I think about it. Maybe? Is this both vector and tuple deconstruction? I can't remember if this is how it's done in this particular language, but I'd hope that is a feature. That would be a useful feature for something that I can think of, but you know. Right, I'm just going to say yes to this. I see no reason why not. This is vector and tuple deconstruction, ignoring any value off of n. This, I believe, will work. To the fact that it's ignoring the first value and taking in the second. Perhaps not. No, it's in a. Okay, that's not something I need. Sorry about that. No, actually, I don't think that'll work because this is a vector. I don't think you can deconstruct like that. Never mind. Glad I rechecked. Then we have just. Maybe this does work? I don't think so. I'm just going to say the first and last work. This may work because it may just be ignoring the entirety of it. But simply setting a value to underscore is telling an LSP not to complain. I believe. That is fine. Determine whether the program will pass the compiler. Right, let x equals sum, a value of sum, which is a reference. Yep, sorry, a reference to an array, sorry, to a vector holding 0 and 1. If x, this will not work, that will not compile. Obviously not. Because just to state the reasoning, we have 1, which is in the center of 2 dot dots. This means ignore everything before and ignore everything after, and 1. The compiler cannot know where 1 is, even if it is just 0 and a 1. And it could obviously be told. If it was 0, 1, 2, 3, 7, it wouldn't know where that 1 piece would be. This would be if there's any 1 inside of it, but that doesn't work for pattern. This can't be actually parsed, I don't believe. The issue isn't that this couldn't work, but I don't believe Rust does work like this. During a parsing stage, you could tell the compiler to just run whatever function, whatever mat function on the vector works to check it, but hey, I don't think Rust does that, nor should it. I like explicitity. Explicitity? I like it being explicit. So, to be clear, no, I do not believe this will compile. There's a fourth question. Say we have a point type with the following definition, x and y. Given the following pattern, which of the following values will match this pattern? So we have x is a type x. Right, so, oh gosh, I cannot remember what the add operator does. Huh. I simply can't remember what the at operator does. Let's see if we can find it here. This is cheating, by the way. The at binding lets us create a variable that holds a value at the same time as we're testing that value for a match pattern. Right, ID variable at 3 dot dot dot. As we're testing that value for a match pattern. We want to test message hello ID field, range of 3 to 7. We also want to bind the value to the variable ID variable. All right, so this is creating ID variable. Where is that coming from? Right, yep. Yep, I understand now. I can remember. So we are creating x at... All right, so from the match statement, so we have a match statement. I can see why I don't fully recognize this, because there would be above a match statement on a value, and we're creating a value x, which is bound from 0 all the way to 5. This is a range, and then utilize if x is plus y does not equal 0. Right, so that does make sense to me. X is being bound to the variable matched to. So I think I can go forward with this. Right, will this work? Point x plus equals 5. That is within this range, creating x. I believe that'll work. Am I incorrect on this? Yes, that will work. As long as ID is within that range. This is matching a pattern on x, the x value from there. Also creating the value x, which holds the value x here. Okay. Yep. So this will work, I believe. That's 4 plus -4 plus 5 is 1. So that's fine. Plus it does fit. It does match this statement. And does have a y variable. This will not match because that is not between 0 and 5. This will not match because that is equal to 0. This will match because that is equal to 1. Also is within the range of 0 to 5. I have to just assume that this is inclusive. I forget. Hey, I got one wrong. I think I understand which one is wrong. This one. Ah. Right, I'm not going to understand why without seeing the correct answer. Right. Ah, this one does work. That is what I stated previously. I thought it might work, but hey, we win some, we lose some. Better to believe something won't work than something will work and then checking it. Well, actually, I guess in Rust, where it'll just fail, best to assume something won't work. Something will work and then see it fail on the compiler. Right, let's just read through these questions. This is the correct answer. This will compile and it will go to B because of, well, let's read. The first branch matches y equals 1, which means y does not equal 0, so the pattern fails. The second branch requires that x is equal to 0, which is true, so the pattern succeeds. That is correct, and this is, of course, ignoring the value. Secondarily, we got this incorrect. The pattern underscore and n is not valid because A is an array of tuples, not a tuple itself. Okay, correct. It's not going to describe these, but we can understand this is just, hey, any value. This is any value n within a tuple, which can be any length, within a vector. And this is any vector. These are the patterns. Ah, yes, I remember. This isn't just an identifier, this is a pattern. I can remember now what they are stating. That makes sense. God, I would love to read the parser for this. The lexer, too, God. Well, not the parser, actually, the lexer itself. I would love to see how it tokenizes these pieces. Alright. It is not valid to use ... on both sides. Ah, yeah, as we had stated. Since it is ambiguous, which array element is being referred to? This is for question 3. We are simply saying that it will not compile at this point, because it can't tell where that one is supposed to be. Alright, question 4. Say we have a... Right, we've already got this. We got this correct. The reasoning for that is the pattern specifies x must be between 0 and 5 inclusive, and then x plus y does not equal 0. Therefore, 5, -4, and 0, 1 are valid. Well, -1, 2, and 3, -3 are not. Summary. Rust patterns are very useful in distinguishing between different types of data. When used in match expressions, Rust ensures your pattern will cover every possible value, but your program won't compile. Patterns in let statements and function parameters make those constructs more useful, enabling the destructuring of values into smaller parts at the same time as assigning to variables. We can create simpler complex patterns to suit our needs. Next, for the penultimate chapter of this book, look at some advanced aspects of the We'll look at some advanced aspects of a variety of Rust's features. Right. Advanced features. By now, you've learned the most commonly used parts of the Rust programming language. Before we do one more project in Chapter 20, we'll look at a few aspects of the language you might run into every once in a while, but may not use every day. You can use this chapter as a reference for when you encounter any unknowns. Unlike the other chapters, we got all that down pat. Ignore the past 28 videos that I have on this. Ignore those. The features covered here are useful in very specific situations. Although you might not reach for them often, we want to make sure you have a grasp of all features Rust has to offer. In this chapter, we'll cover unsafe Rust, how to opt out of some of Rust's guarantees and take responsibility for manually upholding those guarantees. Advanced traits, associated types, default parameters, fully qualified syntax, super traits, and the new type pattern in relation to traits. Advanced types, more about the new type pattern, type aliases, the never type, and dynamically sized types. Oh, I wonder if this is kind of just like C, where the end piece can be dynamic as long as it's a specific data type. Or if they've got some weird stuff about it. I hope they have some weird stuff about it. C, dynamically sized types suck. Advanced functions and closures, function pointers and returning closures, as well as finally macros, ways to define code that defines more code at compile time. This will be seen a lot more than you think. Unless Rust just has everything out of the box, you'll see this a lot, especially if you start building your own programs. But I suppose if you're using other people's programs or simply contributing to them, they've already built their own macros. Right? It's a panoply of Rust features with something for everyone. Let's dive in. These pieces of trash. I barely passed grade 5 English. I failed grade 9. That's a lie. Unsafe Rust. All the code we've discussed so far has had Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called Unsafe Rust, and works just like regular Rust, but gives us superpowers. Unsafe Rust exists because, by nature, static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some valid programs than to accept some invalid programs. Although the code might be okay, if the Rust compiler doesn't have enough information to be confident, it will reject the code. In these cases, you can use unsafe code to tell the compiler, trust me, I know what I'm doing. Be warned, however, you do not know what you're doing. This is a lie, you've deluded yourself, and you will fail. Also separately, that you use unsafe Rust at your own risk. Oh, no shit. If you use unsafe code incorrectly, problems can occur due to memory unsafety, such as a null pointer dereference. Another reason Rust has an unsafe alter ego is that the underlying computer hardware is inherently unsafe. If Rust didn't let you do unsafe operations, you couldn't do certain tasks. Rust needs to allow you to do low-level systems programming, such as directly interfacing with the operating system or even writing your own operating system. Working with low-level systems programming is one of the goals of the language. Let's explore what we can do with unsafe Rust and how to do it. Alright, so we got these superpowers. To switch to unsafe Rust, use the unsafe keyword, and then start a new block that holds the unsafe code. You can take 5 actions in unsafe Rust that you can't in safe Rust. We'll call these unsafe superpowers. I hate the framing. These superpowers include the ability to dereference a raw pointer, call an unsafe function or method, access or modify a mutable static variable, implement an unsafe trait, and separately access fields of union. Lastly, you can walk through walls, disappear, and fly. Right. That's fine. It's important to understand that unsafe doesn't turn off the border checker or disable any other of Rust safety features. If you use a reference in unsafe code, it will still be checked. The unsafe keyword only gives you access to these 5 features that are then not checked by the compiler for memory safety. You'll still get some degree of safety inside of an unsafe block. That's good to know. In addition, unsafe does not mean the code inside the block is necessarily dangerous, or that it will definitely have memory safety problems. The intent is that, as the programmer, you ensure the code inside an unsafe block will access memory in a valid way. People are fallible, and mistakes will happen, but by requiring these 5 unsafe operations to be inside the blocks annotated with unsafe, you know that any errors related to memory safety must be within an unsafe block. Keep unsafe blocks small. You'll be thankful later when you investigate memory bugs. To isolate unsafe code as much as possible, it's best to enclose unsafe code within a safe abstraction and provide a safe API, which we'll discuss later in the chapter when we examine unsafe functions and methods. Parts of the standard library are implemented in a safe abstraction over unsafe code that has been audited. Wrapping unsafe code in a safe abstraction prevents use of unsafe from leaking out into all the places that you or your other users might want to use the functionality implemented with unsafe code. Because using a safe abstraction is safe. Let's look at each of the 5 unsafe superpowers in turn. We'll also look at some abstractions that provide a safe interface for unsafe code. Okay, we are going to dereference a raw pointer. In Chapter 4, in the Dangling References section, we mentioned that the compiler can assure references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to references. As with references, raw pointers can be immutable or mutable and are written as either dereference const and isn't that the dereference operator? I'm an idiot. And dereference mut t. Thank you. Later on it does state the asterisk isn't a dereference operator. It's part of the type name. And I hate it. That disgusts me. Why? Why? That's incredibly confusing. In the context of a raw pointer, immutable means that the pointer can't be directly assigned to after being dereferenced. Right. In the context, immutable means the pointer can't be directly assigned to after being dereferenced. Oh, okay? Sure. Different from references and smart pointers, raw pointers are allowed to ignore the boring rules by having both immutable and mutable pointers or multiple mutable pointers to the same location. They separately aren't guaranteed to point to valid memory. Sure. Are allowed to be null. That's bad. And don't implement any automatic cleaning. Okay? By opting out of having Rust it has a little bit of an automated cleanup, but that's really the operating system itself. If your application quits out, unless of course you're at the kernel level, if your application quits out, the operating system will clean up any memory. By opting out of having Rust enforce these guarantees, you can give up guaranteed safety in exchange for greater performance or the ability to interface with another language or hardware where Rust guarantees do not apply. Listing 19.1 shows how to create an immutable and mutable raw pointer from references. Right. So we have let mutable number equal 5, let reference 1 equal a reference num as a raw pointer, an immutable raw pointer of type i32. Separately, let r2 equal a reference, which is mutable, to num as a mutable i32 raw pointer. Notice that we don't include the unsafe keyword in this code. That is true. We can create raw pointers in safe code. We just can't dereference raw pointers outside of an unsafe block, as you'll see in a bit. Okay, that does make sense. If you're not doing any dereferencing with these things, you can even do work with them. They're not really doing anything that could damage us. That's not unsafe at all. You could just add one to these pointers, make it have memory that you may not even own or other parts of your piece, and it would probably be fine, as long as you don't dereference them. We've created raw pointers using as to cast an immutable and mutable reference into their corresponding raw pointer types. Because we created them directly from references guaranteed to be valid, we know these particular raw pointers are valid. But we can't make that assumption about just any raw pointer. To demonstrate this, next we'll create a raw pointer whose validity we can't be so certain of. Listing 19.2 shows how to create a raw pointer to an arbitrary location in memory. Trying to use arbitrary memory is undefined. Undefined behavior, by the way, is just it's a bug, it's a failure, it's something that cannot be described. There might be data at that address, or there may not be. The compiler might optimize the code so there is no memory access, or the program might error with a segmentation fault. Usually, there's no good reason to write code like this, but it is possible. Usually correct, however, in the embedded world where you know exactly how much memory you have, you could utilize this, like if you're building like something for a smart fridge or something for a stove with a little clock on it. You could store things at specific pieces of memory so that you don't really have boundaries. You could store something like is on as just a single byte in like one of the first pieces of location. This is perfectly reasonable for things where you need to be really small with your code, or things where only your application is going to be run. It is possible that this is useful. Yeah, that's why this says usually there's no good reason to write code like this. There can be, but you're never going to run into it. You're not going to write for embedded systems. And if you do, well, good on you. Creating a raw pointer to an arbitrary memory address. We simply, hey, have this. We have the hex code, 0, 1, 2, 3, 4, 5, which funnily enough is not actually 1, 2, 3, 4, 5. I don't know why I said that, but yeah, that's not 1,000 or 12,345. That's since this is a hex value. I don't know why I'm describing this, but this is a use size. Recall that we can create raw pointers in unsafe code. Oh. Really? That's all we do? That's how we create it? What if we had the value within hex code, which is a use size here, and we want to have that value? Well, I don't actually see any use for that. I see no real use for that. No, I really don't. Okay, yeah, I guess I just like things being a bit more explicit, but yeah, that is fair. We are simply having address as const as an immutable raw pointer. I32. So that, oh my lord, no, I am an idiot. No, I am a fool. Sorry, I am wrong. Right, so if we wanted just this as a value, we would have a reference to the address as the const, so on and so forth. So the reference would be a pointer, which is created by, well, Rust, the language, that then is passed in as this value. Sorry, I'm a bit of a fool. That is correct. Recall that we can create raw pointers in unsafe code, but can't dereference raw pointers and read the data being pointed to. In listing 19.3, we'll use the dereference operator, dereference, on a raw pointer that requires an unsafe block. Let mutable number equal 5. Then we have R1 equal a reference to num as a constant as an immutable raw pointer of type I32. Or well, I32 would... oh, whatever. And we have the same thing here. Then within the unsafe code, we are allowed to utilize this. We are allowed to dereference it and get 5 back. If we run this, we're going to get 5 and 5, I believe. Yep. Dereferencing raw pointers with an unsafe block. Creating a pointer does no harm, and it's only when we try and access the value that it points at that we might end up dealing with an invalid value. Can we add to this? Could we... I don't mean like add to 5, which would need dereferencing, but could we add to the pointer itself? Could we change 0, 1, 2, 3, 4, 5 to 0, 1, 2, 3, 4, 6 in an unsafe bit of code? Because that's just changing where the memory exists. or sorry, what memory is pointing to. It's not actually utilizing it. It's not technically unsafe. Creating a pointer, yep. Note also that in listing 19.1 and 19.3, we created an immutable pointer and a mutable pointer, raw pointer, that both pointed to the same memory location, where num is stored. If we instead tried to create an immutable and mutable reference to num, the code would not have compiled, because Rust ownership rules don't allow a mutable reference at the same time as any immutable reference. With raw pointers, however, we can create a mutable pointer and an immutable pointer to the same location and change data through the mutable pointer, potentially creating a data race. Be careful. This is useful in very small situations, like again embedded data, where you'd have one interface that can simply only read the data, and then a second interface which is responsible for changing the data. The mutable reference can be utilized to change the value that an immutable reference references. However, you could have at any point in your code this immutable reference and ensure that it is not changed by some rando who comes in to read the code. And also that you know at all points where this data could be changed. With all of these it is Tuesday. Yeah. I'm messed up. It was Labor Day yesterday. Alright, with all these dangers, why would you ever use raw pointers? One major use case is when interfacing with C code, which only has raw pointers, as you'll see in the next section, calling an unsafe function or method. Another case is when building up safe abstractions that the borrow checker doesn't understand. We'll introduce unsafe functions and then look at an example of a safe abstraction that uses unsafe code. Right, calling an unsafe function or method. The second type of operation that you can perform in an unsafe block is called unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements we need to uphold when we call this function. Because Rust can't guarantee we've met these requirements. By calling an unsafe function with an unsafe block, we're saying that we've read this function's documentation and take responsibility for upholding the function's contracts. Here is an unsafe function named dangerous that doesn't do anything in this body. Right, so we have said that this function is unsafe, and have named it dangerous. Then we call dangerous within an unsafe block. So we can name this without being directly in an unsafe block. However, in order to use it, we must be in an unsafe block. Though I guess you could say that this entire block is unsafe. Oh, well, I mean, kind of makes sense. This is just a syntax. Sorry, not a syntax. What is it called? The word for it is leaving me right now. I guess I can't make that point. Sorry about that. We must call the dangerous function within a separate unsafe block. If we try to call dangerous without the unsafe block, we get this error. What is here? Call to unsafe function dangerous is unsafe and requires unsafe function or block function. And requires unsafe function or block. Oh, and requires an unsafe function or block, as in like, you could call dangerous within a function that is unsafe, or separately it must be within this unsafe block. Right. With the unsafe block, we're asserting to Rust that we read the function's documentation, we understand how to use it properly, and we've identified that we're fulfilling the contract of the function. Bodies of unsafe functions are effectively unsafe blocks, so to perform other unsafe operations within an unsafe function, we don't need to add another unsafe block. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark the entire function as unsafe. In fact, wrapping unsafe code in a safe function is a common abstraction. As an example, let's study the split at mute function from the standard library, which requires some unsafe code. we'll explore how we might implement it. This safe method is defined on mutable slices. It takes one slice and makes it two by splitting the slice at the index given as its argument. Listing 1914 shows how to use split at mute. Alright, so we have split at mute 3, which at the third indices splits. So after 0, 1, 2, 3, it'll split. No, it won't. Index of a given argument. What? 0, 1, 2, 3. Okay, yeah, so I guess it splits before the index of the given mutices. Mutices? Index, sorry, I don't know why I said mutices for. Apologies. Don't even know what that word means. Anyway, just to say here, we have let mutable v equal a vector of 0, 1, 2, 3, 4, 5, and 6, which is then let r equal a reference to the immutable reference to v, and then the entire thing. So we are taking a split of the vector v, and a split contains everything. Let a and b equal. Alright, so split at mute will output a tuple, which will be two different splits, I would assume, of v. I hate how they took out that bit where you could just hover over something to get the documentation. We can't implement this function using only safe Rust. An attempt might look something like listing 19.5, which won't compile. For simplicity, we'll implement split at mute as a function rather than a method, and only for slices of i32 values rather than the generic type t. Right, so here we have function split at mute. We've taken the values and the middle. Or sorry, it doesn't need to be the middle, but the place where we will intersect. And we return a tuple with a mutable reference to a vector of i32s. Right. So let length equal the entire length. Assert that the middle is less than or equal to length. Then the first is a split of everything until the mid, and everything after the mid is another split here. This here is two mutable references to the same value. This is why, to the same, not to the same value, but to the same original option, to the same original v here, the same original vector. We will now have two mutable references active at the same time. That is a failure within Rust. We cannot do that. This function first gets the total length of slice. Then it asserts that the index given as a parameter is within the slice by checking whether it's less than or equal to the length. The assertion means that if we pass an index that is greater than the length to split the slice at, the function will panic before it attempts to use that index. Then, we return two mutable slices in a tuple. One from the start of the origin slice to the mid index, and another from mid to the end of the slice. When we try and compile, however, it'll tell us, hey, error, cannot borrow the reference values as mutable more than once at a time. There's the location. It says, returning this value requires that dereference values is borrowed for 1, for a lifetime of 1. Here is where the first mutable borrow occurs, and here is where the second one occurs. Thus we have two mutable references, and we falter, we fail. Rust's first borrow checker can't understand that we're borrowing different parts of the slice. It only knows that we're borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay, because the two slices aren't overlapping. But Rust isn't smart enough to know this. Well, when we know code is okay, but Rust doesn't, it's time to reach for unsafe code. Listing 19.6 shows how to use an unsafe block, a raw pointer, and some calls to unsafe functions to make the implementation of split at mute work. Using standard slice, function split at slice, we take in. Right, so it's essentially the same. I always forget the word. It's the same pattern, not pattern as in Rust patterns, but it's the same everything else. We have the same here. We have a length equal value.length. Secondarily, we have let pointer equal values.asMutable pointer. So that will be a pointer to values, a mutable pointer. Now we assert that mid is of course less than or equal to length. Right, within the unsafe, slice from raw pointer from raw parts mutable. We are not familiar with these functions, and thus must assume that they do what previously had been done. We simply take the pointer to the midpoint to create a new slice from raw parts mute. Sure. And then here is pointer to the values dot add mid. Oh, yeah. Okay, really? There's a whole function to add to the pointer? That's kinda dumb. If we're in unsafe code, we should know what we're doing. Why is there a function for add? I'm really curious on that. Right, to be clear, a pointer is just a reference to a cubbyhole, essentially. A name tag on a big wall of cubbyholes with a number on it which references it. A vector stores things in cubbyhole, 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 right next to each other. So we are simply taking a pointer, which is a number. My hands are not going over, but we're simply taking pointer, which is a number, and then adding 1, 2, 3 over to it to get the third hole, the third bit of memory to the right of that pointer. Why can't we just do pointer equals pointer plus the original bit? Or just here, pointer plus mid. What would be the issue with that? Of course, we would have to cast mid over to its hex value, to a usize value, which wouldn't be hard to do. It's just a simple cast. Why do we need a function here? I think that's dumb. Right. And then secondarily, we're taking the length minus the mid. Right, yep. Huh. Why? Length is the entire thing, so if there are 5 values, that would be 5 minus the middle point, which is 3. I guess that's how many from this point we want. I get that. Okay. So this would be saying, hey, get us the next blank amount. To the mid. Right, yep, that makes sense. Yeah, because that could be any size. Because we've already done the mid. We've already taken the values up to the midpoint, and then we want to take everything past that. And thus the amount left would be length minus the mid. Sorry about that. Recall from the slice type section chapter 4 that slices are a pointer to some data and the length of the slice. We use the length method to get the length of the slice and the as mutable pointer method to access the raw pointer of a slice. In this case, because we have a mutable slice to either to 2 values, as mutable pointer returns a raw pointer with the type mutable raw pointer, which we stored in the variable pointer. We keep the assertion that the mid index is within the slice. Then we get to the unsafe code. The slice from raw parts mute function takes a raw pointer and a length and creates a slice. We use this function to create a slice that starts from pointer and is mid items long. Then we call the add method on pointer with mid as an argument to get a raw pointer that starts at mid. And we create a slice using that pointer and the remaining number of items after mid as the length. Okay. The function slice from raw parse mute is unsafe because it takes a raw pointer and must trust that the pointer is valid. We could just add 9,000 to it every single time and get the 9,000th value from this point. The add method on raw pointers is also unsafe because it must trust that the offset location is also a valid pointer. Yep. Therefore, we add an unsafe block around our calls to slice from raw parse mute and add so we can call them. By looking at the code and by adding the assertion that mid must be less than or equal to length, we can tell that all raw pointers used within the unsafe block will be valid pointers to data within the slice. This is an acceptable and appropriate use of unsafe. Note that we don't need to mark the resulting split at mute function as unsafe, and we can call this function from safe rust. We've created a safe abstraction to the unsafe code with an implementation of the function that uses unsafe code in a safe way, because it creates only valid pointers from the data this function has access to. In contrast, the use of slice from raw parse mute in listing 19.7 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice 1000 items long, as I previously stated. Right, yep, we have used and a slice, let address equal this specific random address, let r equal address is, yep. And values I32 unsafe slice from raw root parts mute. This will likely crash when the slice is used. Would it? Yeah, it would. Depending on how. Likely. Right. So this is simply trying to access a random arbitrary address, even if we ignore that and it was a real address. It is trying to access 1000 off of it, which is very unlikely to be what we want. We don't own the memory at this arbitrary location, and there's no guarantee that the slice this code creates contains a valid I32 value. Attempting to use values as though it's a valid slice results in undefined behavior. Using extern functions to call external code. Sometimes your Rust code might need to interact with code written in another language. For this, Rust has the keyword extern that facilitates the creation and use of a foreign function interface. An FFI is a way for a programming language to define functions and enable a different foreign programming language to call those functions. Listing 19 through 8 demonstrates how to set up an integration with the ABS function from the C standard library. Functions declared with extern blocks are always unsafe to call from Rust code. The reason is that other languages don't enforce Rust rules and guarantees, and Rust can't check them, so responsibility falls on the programmer to ensure safety. That makes complete sense. Even languages which do implement some type of a borrow checker or some type of memory safety, perhaps you're doing it with a C++. Rust doesn't know that you are utilizing these in the same way as that would assume you would. You're just getting a value back. Right, so we have extern for C. Okay, so extern is likely some weird form of macro or something that picks in a string of any language of that type with a list of languages. I have no idea. That is a strange syntax. Function ABS input. Right, so as long as the input is an I32 and the output is an I32. Okay, sure. Absolute value of -3 according to C is ABS -3. Right, so is what this is doing. Do you need C the language to be able to work on your computer? Do you need GCC? Where is it getting this from? Has for every single piece of code C can utilize Rust implemented some weird interface? What's going on here? Is this full? This is the full code. This is the full code. Really? How does that work? Is it binding ABS, the function, to the ABS function in C? What if you're bringing in some library from C or some other function? How do we bring that in? Or some application, how do we bring that in? With the extern C within the string C block, we list the names and signatures of external functions from other languages we want to call. I always forget the word signatures, my lord. The C part defines which application binary interface. So that's a string, which is simply going to use C doesn't do anything. Sure. So that's probably a binary built in with Rust itself, but you can probably build your own. The external function uses. The ABI defines how to call the function at the assembly level. The C ABI is the most common and follows the C programming language's ABI. Okay? calling Rust functions from other languages. We can also use extern to create an interface that allows other languages to call Rust functions. Instead of creating a whole extern block, we add the extern keyword and specify the ABI to use just before the function keyword to the relevant function. We also need to add a no mangle annotation to tell the Rust compiler not to mangle the name of this function. Mangling is when the compiler changes the name we've given a function to a different name that contains more information for other parts of the compilation process to consume less. For other parts of the compilation process to consume, but is less human readable. Every programming language compiler mangles names slightly differently. So for a Rust function to be nameable by other languages, we must disable the Rust compiler's name mangling. Okay? In the following example, we make the call from C function accessible from C code, after it's compiled to a shared library and linked from C. Right, how do you do that in Rust? How do we compile Rust to a shared library and link it? How do we compile C from shared library and link it to Rust? That's really what I'd want to do. Well, no, I could see a use case for this exact thing, yeah, if I'm just trying to slowly convert over a C project to Rust. Right, so, mangle pub extern C function call from C. Right, we just called a function from C. This usage of extern does not require unsafe. No, because there's no unsafe code here. It's just Rust. I mean, you can use unsafe later on in it, but this is not necessarily unsafe. Nope. Accessing or modifying a mutable static variable. So we're just going to move on. How is this supposed to be used as a reference? How do I actually do this? I mean, I can understand that just putting C in here will in fact allow me to use any function from just the C standard library, but why would I want that? That is useless to me. I would want to call things from, like, actually written C code. Alright, I guess I'd have to find out how to use an ABI and then put that into my path, or allow that to be utilized by Rust in some form. Alright, whatever. Right, accessing or modifying a mutable static variable. In this book, we've not yet talked about global variables, which Rust does support, but can be problematic with Rust ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. In Rust, global variables are called static variables. Listing 19.9 shows an example declaration and use of a static variable with a string slice as a value. Right, so we've got static hello world, all capitalized with an underscore good, which is a reference string or a string slice from hello world. Right, and we have function main, print line, name is, and then we insert hello world. Static variables are similar to constants, which we discussed in the differences between variables and constants section in chapter 3. The name of static variables are in Screaming Snake Case by convention. I love that name. Static variables can only store references with the static lifetime, which means the Rust compiler can figure out the lifetime, and we aren't required to annotate it explicitly. Accessing an immutable static variable is safe. A subtle difference between constants and immutable static variables is that values in a static variable have a fixed address in memory. Okay. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they're used. Another difference is that static variables can be mutable. Accessing and modifying mutable static variables is unsafe. Listing 1910 shows how to declare, access, and modify a mutable static variable named counter. Static mute counter, which is U32, equals 0. We have a function which houses an unsafe bit of code, which just adds the increment to counter. We have function main, add to count 3, and we print the counter. Now, this is very likely going to be a perfectly safe utilization of this. Race conditions are where we have one piece which changes a variable and another piece which changes a variable, and they may change that variable at a different point in time. And thus, accessing it at two different points will give us two different situations. That'll give us two different outcomes. Now, with counter, that's simply going to count up every time something happens. It's very unlikely that it's going to be utilized, that that's going to have any issue, even if it's done at the same time. So that was not a good explanation, but what am I going to do with that? As with regular variables, we specify mutability using the mute keyword. Any code that reads or writes from counter must be within an unsafe block. This code compiles and prints counter 3, as we would expect because it's single-threaded. Having multiple threads access counter would likely result in data races, which isn't necessarily bad for counter. Like, as long as it's accessing it and it's not going to be trusting that only the amount that you have added within that specific thread is counted, it should be fine. With immutable data that is globally accessible, it's difficult to ensure there are no data races, which is why Rust considers mutable static variables to be unsafe. Where possible, it's preferable to use concurrency techniques and thread-safe smart pointers we discussed in Chapter 16, so the compiler checks that data accessed from different threads is done safely. Implementing an unsafe trait. You can use unsafe to implement an unsafe trait. A trait is unsafe when at least one of its methods has some invariant that the compiler cannot verify. We declare that a trait is unsafe by adding the unsafe keyword before trait, and marking the implementation of the trait as unsafe too, as shown in listing 1911. Unsafe trait foo method goes here. Unsafe implements foo for I32. Then we have an implementation of the trait, which is unsafe. Defining and implementing an unsafe trait. By using unsafe impl, we're promising that we'll uphold the invariant that the compiler can't verify. As an example, recall the sync and send marker trait we discussed in the extensible concurrency with the sync and send traits section in Chapter 16. The compiler implements these traits automatically if our types are composed entirely of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, and we want to mark that type as send or sync, we must use unsafe. Rust can't verify that our type upholds the guarantees that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do these checks manually and it indicates as such with unsafe. Alright. Accessing fields of a union. The final action that works with unsafe is accessing fields of the union. A union is similar to a struct, but only one declared field is used in a particular instance at one time. Unions are primarily used to interface with unions in C code. Accessing union fields is unsafe because Rust can't guarantee the type of the data currently being stored in the union instance. You can learn more about unions in the Rust reference. When to use unsafe code, the final thing before we go to the quiz. Using unsafe to take one of the 5 action superpowers we discussed isn't wrong or even frowned upon, but it's trickier to get unsafe code. But it is trickier to get unsafe code correct because the compiler can't help uphold memory safety. When you have a reason to use unsafe code, you can do so, and having the explicit unsafe annotation makes it easier to track down the source of problems when they occur. Right, and we finally got this quiz. Fantastic. I'm terrified. Did I actually learn anything? Just a moment. I'm going to sit down. I've been standing for too long. Can you see me? No, you cannot. Oh no, I must go down. Huh? Oh, was that me? Oh, it's me. I'm back. Right. Which of the following are superpowers that Rust enables inside of an unsafe block? Calling a function, mark as unsafe. Yep. Dereferencing raw pointers. Yep. Converting a reference to a raw pointer. Nope. Disabling the borrow checker. Nope. I believe calling a function that is marked unsafe is a superpower, but I'm unsure if that was explicitly stated in the superpower section. Right, determine whether this will pass the compiler. Right, so we have a mutable vector v with a capacity of 4. 4, 0 to 3, push I. So that's 0, 1, 2, and 3. Right, so let n equal a reference to v, let n equal a raw pointer immutable to the 0th element within the vector v. v.push 4. We cannot push anything here. Can we? We have a raw pointer here, which is a reference to it. Will this compile? I don't see why not. Right, so it didn't explicitly tell us whether or not... Well, this is an immutable reference to it, so it should be fine even if that was just a regular reference to that bit. I believe that will compile, and it will still give us the 0th element, which should be 0. No, it will not. No, because v is destroyed. I'm an idiot. V is destroyed at this point, but we have a reference here. Wait, will it compile? Huh. It shouldn't work. And by shouldn't work, I mean this will cause a memory error. We are accessing random memory. Will it protect us? I guess it will, because the borrow checker still works. But raw pointers specifically don't like that. Alright, that will break. No matter what, that will break, and I could not actually give you the output, because the output could be an error. That could be anything. But the issue here is that at this point it destroys v, and we still have an active reference to v here. And then we are using said active reference. That does not compile. I'm going to have to assume, because I couldn't tell you what it actually does. Which of the following are situations where using unsafe code, or a safe wrapper around unsafe code, is an idiomatic method for working around the borrow checker? Right, they're turning a pointer to a stack allocated variable out of a function. Nope. Getting two mutable references to disjoint indices of an array. Yes. Allowing values to be uninitialized when they are not being read. I don't even know what that means. I don't know what that means. Having a reference to one field of a struct sit in another field of the same struct. Can you not do that? I don't see why you couldn't do that. Ah, sure, let's use that. Right, I got one of them correct. Yep, this is correct, but the rest are not. This program does compile? What is the output? It compiles, and it'll be 0, but it's destroyed. So that'll update to the new value? This program is dangerous. It compiles correctly and executes without issue because VEC has enough capacity. Okay. Really? Okay, so capacity... I guess I misunderstood with capacity. I thought that there were 0, 1, 2, and 3, which are 4 different pieces, but with capacity must give you 5 different pieces from that 4 being put in there. With capacity for up to the index 4, I guess? I guess. Sure, whatever. Unless that is non-inclusive. That's not inclusive. That's not inclusive. I don't think. Whatever it is, okay. However, if the capacity were 3, then n would point to deallocated memory. Right? I got this wrong. I'm going to guess without looking at it. Nope, I can't guess because I got one wrong. There's one that I missed, right? Getting 2 mutable references is correct, and having a reference is correct, allowing values to be uninitialized when they are not being read. That is also fine. I honestly don't understand what that is. Context: 2 immutable references to disjoint indices are reasonable because the border checker doesn't understand when indices are disjoint. See, split at mute. Allowing values to be uninitialized is reasonable because the border checker adopts a conservative policy that values must always be initialized. Oh, yeah, that's fair. Yeah, I forgot you can't actually have an uninitialized variable, right? But it's sometimes useful to work with uninitialized variables. See, maybe uninit and the take mutable create. General assumes that a variable is properly initialized according to requirements. For example, a variable of reference type may be a line and non-null. This is an invariant that must always be upheld, even in unsafe code. As a consequence, zero initializing a variable of reference type causes instantaneous undefined behavior, no matter whether that reference ever gets used to access memory. This is exploited by the compiler for various optimizations, such as eliding runtime checks and optimizing enum output. Similarly, entirely uninitialized memory may have any content. Well, a bool must always be true or false. Hence, creating an uninitialized bool is undefined behavior. Right, are you going to describe why this is useful? I've stopped there. Right. Having a struct uphold a reference to itself is I do now understand what that means. Yeah. So let x. X doesn't have any value. Having a struct hold a reference to itself is reasonable because the border checker cannot reason about the lifetime of a self-reference. See standard pin module. However, returning a pointer to a stack allocated variable is never valid to do with unsafe code. The only appropriate workaround is to use garbage collection. For example, returning an RC instead of a reference T. Oh, okay, I guess you can't do that normally. Why not? I guess because it's on the stack? I don't understand. Sure. Right, returning a pointer to a stack allocated variable. Oh, no, that's not going to work, of course. Because the stack's dead. You've returned. Sure. Right, advanced traits. Right. So it's 8:43? We've still got some time. How long is advanced traits? Ooh, we're definitely not going to get through all of this. Well, we could actually in the time given to us, 45 minutes. Let's start. Advanced traits. We first covered traits in the Traits, Defining Shared Behavior section of Chapter 10. But we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty-gritty. Specifying placeholder types in type definitions with associated types. Sorry, just a moment. Associated types connect a type placeholder with a trait, such that the trait method definitions can use these placeholder types in their signatures. The implementer of a trait will specify the concrete type to be used instead of the placeholder type for the particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We've described most of the advanced features in this chapter as being rarely needed. Associated types are somewhere in the middle. They're used more rarely than features explained in the rest of this book, but more commonly than many of the other features discussed in this chapter. One example of a trait with an associated type is the iterator trait that the standard library provides. The associated type is named item and stands in for the type of the value. The type implements the iterator trait. The associated type is named item and stands in for the type of the values the type implementing the iterator trait is iterating over. Okay? The definition of the iterator trait is as shown in listing 1912. Right, public trait iterator, type item. Function next is a mutable reference to self. Right, taking in a mutable reference to self, sorry. outputting an option holding self item. Okay? The definition of the iterator trait that has an associated type item. The type item is a placeholder, and the next method's definition shows that it will return values of the type option self item. Implementers of the iterator trait will specify the concrete type for item, and the next method will return an option containing a value of that concrete type. Associated types might seem like a similar concept to generics. In that the latter allows us to define a function without specifying what types it can handle. To examine the difference between two concepts, we'll look at an implementation of the iterator trait on a type named counter that specifies the item type as U32. Right, implement iterator for counter. Type item is equal to an AU32. Right, and then the function next is a mutable reference to self, outputs an option holding self item. Okay. And then here is the actual function. The syntax seems comparable to that of generics, so why not just define the iterator trait with generics as shown in listing 1913? Well, because you might have other code that will check for a counter item, which needs to be a U32 in this instance, but may be a generic of anything else. Right. Here's public trait iterator function next, a mutable reference to self outputting an option of any type. The difference is that when using generics, as in listing 1913, we must annotate the types in each implementation, because we can also implement iterator string for counter, or any other type. We could have multiple implementations for iterator for counter. So we could have this, but also separately we could have I don't know why I'm explaining this further. That is fairly understandable. We could have two different things. If we pass in a U32 or a string, it can do things differently. However, here we are ensuring that we only have one implementation of the next method, which outputs an option with one different value. Okay? Because we can also, we can have multiple implementations for, right. In other words, when a trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic type parameters each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associated types, we don't need to annotate types because we can't implement a trait on a type multiple times. And listing 1912, with the definition that uses associated types, we can only choose what the type of item will be once, because there can only be one impl iterator for counter. We don't have to specify that we want an iterator of U32, values everywhere that we call next on counter. Okay. Associated types also become part of the trait's contract. Implementers of the trait must implement a type to stand in for the associated type placeholder. Associated types often have a name that describes how the type will be used, and documenting the associated type in the API documentation is good practice. Okay. Default generic type parameters and operator overloading. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type if the default type works. You specify a default type when declaring a generic type with the placeholder type equals concrete type syntax. A great example of a situation where the technique is useful is with operator overloading, in which you customize the behavior of an operator, such as plus, in particular situations. Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations with corresponding traits listed in standard ops by implementing the trait associated with the operator. For example, in listing 1914, we overload the plus operator to add two point instances together. We do this by implementing the add trait on the point struct. Okay. That's really cool. So that's how operator overloading. That's a strange way of using operator overloading. I like that. Right. So use standard ops add, drive, debug, copy, clone, partial equality, point, x, and y. I'm guessing that add necessitates at least partial equality, clone, and copy. Implement add for point. Type output equals point. All right, so this is the usage of what we had previously described. We have a function add which takes in self and another point and outputs a point. The point x, point x, which is self.x plus other.x. So that's, yep, pretty simple. The current plus the next. And then we have the same here. Function main. Assert equals. Yep. Point x plus 1 equals, x plus 1, y plus 0, plus point x plus 2, y plus 3. Right? Oh, we are creating another point here, to be clear. And that will equal exactly x3, y3. Yep. The add method adds the x values of 2 point instances and the y values of 2 point instances to create a new point. The add trait has an associated type named output that determines the type returned from the add method. That is fairly reasonable. That's cool. The default generic type in this code is within the add trait. Here is the definition. We have the trait add, RHS equals self, right hand side, by the way, equals self. Must implement the type output, which is implemented here. We have the function add, taking in self and right hand side, which is right hand side, and outputting self.output. Right. Oh, so right hand side must be the same type as whatever whatever self is. Sorry, I don't know why I didn't get that. Right, so you have to add two different. Sorry, they have to be the same type, is what it is stating. This code should look generally familiar. A trait with one method and an associated type. The new part is right hand side equals self. This syntax is called default type parameters. The right hand side generic type parameter, short for right hand side, defines the type of the RHS parameter and the add method. We don't specify a concrete type for right hand side when implementing the add trait. The type of right hand side will default to self, which will be the type we're implementing add on. When we implement add for point, we use the default for RHS because we wanted to add 2 point instances. Oh, that's the default. Yeah, sorry. That is true. We'll look at an example of implementing the add trait where we want to customize the RHS type instead of using the default. We have 2 structs, millimeters and meters, holding values in different units. This thin wrapping of an existing type in another struct is known as the new type pattern, which we describe in more detail in the Using the new type pattern to implement external traits on external types section. As quite a name, we want to add values in millimeters to values in meters and have the implementation of add do the conversion correctly. We can implement add for millimeters with meters as the right-hand side, as shown in listing 1915. Alright. So we have standard library right-hand side.rs. We take in a struct millimeters, which is of the type U32, a struct meters, which is of the type U32. Implement add meters for millimeters. Sorry, add, taking in type millimeters for millimeters. So, yep, add. Yeah, so we are passing meters to add as the type for RHS, or right-hand side. I see. So that can be meters. Right. That is for the generic, the type generic, which defaults to the type which is being implemented for millimeters, or self in that case. Right. We are defining outputs as millimeters because we are defining this on millimeters. So the output will be in millimeters. Function add self, taking in self, and the other, which is meters, outputting millimeters. Millimeters dot self 0. Sorry, what? Yeah. That's that. Yep. Millimeters self 0 plus other 0 times 1000. Because it is a meter, so 1 meter is 1000 millimeters. We simply add the value in millimeters to the value in meters times 1000. And how that would be done would be just like uh, let x equal millimeters 7 and let x meters equal, let y equal meters 12, and then we would just do x plus y, and add would be run here. All right. To add millimeters and meters, we specify implement add meters to set the value of the right-hand side type parameter instead of using the default of self. You'll use default type parameters in two main ways: to extend a type without breaking existing code, to allow customization in specific cases most users won't need. The standard library's add trait is an example of the second purpose. Usually, you'll add two like types, but the add trait provides the ability to customize beyond that. Using a default type parameter in the add trait definition means you don't have to specify the extra parameters most of the time. In other words, a bit of implementation boilerplate isn't needed, making it easier to use the trait. The first purpose is similar to the second, but in reverse. If you want to add a type parameter to an existing trait, you can give it a default to allow extension of the functionality of the trait without breaking the existing implementation code. Right. Fully qualified syntax for disambiguation. Calling methods with the same name. Nothing in Rust prevents a trait from having a method of the same name as another trait's method, nor does Rust prevent you from implementing both traits on one type. It is also possible to implement a method directly on the type with the same name as methods from traits. When calling methods with the same name, you'll need to tell Rust which one you want to use. Consider the code in listing 1916, where you've defined two traits, pilot and wizard, that both have a method called fly. We then implement both traits on a type human that already has a method named fly implemented on. Each fly method does something different. So you have pilot, a function, fly, which takes in reference to self, same for wizard, and we have a struct human, implementing pilot for human. Right, implementing the trait pilot for human, having the function fly. This is your captain speaking. Sure, it's just that. Yep, wizard says up, and human says waving arms furiously. Right, there we go. So we have three implementations on human. For a human, which implements pilot, a human, whatever, sure. Two traits are defined to have a fly method and are implemented on the human type. And a fly method is provided on human directly. So this is a default function on human. However, if the human implements wizard, or if the human is a wizard, it's fly, same with pilot. Yep. When we call fly on an instance of human, the compiler defaults to calling the method that is directly implemented on the type, as shown in listing 1917. Yep. Running this code will print waving arms seriously, showing that Rust called the fly method implemented on human directly. To call the fly methods on either pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. Right? So we let person equal human, pilot, fly, and then passing in a reference to person. Same with wizard. And then person.fly. Right. Specifying the trait name before the method name clarifies to Rust which implementation of fly we want to call. We could also write human fly, reference person, which is equivalent to person.fly that we used in listing 1918. But this is a bit longer to write if we don't need to disambiguate. Alright. That works, and it shows you all three different things being put one after the other. Right, because the fly method takes a self parameter, if we have two types that both implement one trait, Rust could figure out which implementation of a trait to use based on the type self. However, associated functions are not methods. Associated functions that are not methods don't have a self parameter. When there are multiple types or traits that define non-method functions with the same function name, Rust doesn't always know which type you mean unless you use fully qualified syntax. For example, in listing 1919, we create a trait for an animal shelter that wants to name all baby dogs Spot. We make an animal trait with an associated non-method function baby name. The animal trait is implemented for the struct dog, on which we also provide an associated non-method function baby name directly. Right, we have trait animal, baby name, outputs a string, struct dog, implementing on dog, baby name, output string, string from Spot. Same with this, we have implement animal for dog, where we have a baby name, outputting string, outputs puppy. So the baby name for animal.dog, passing in dog would be puppy. Yep. Dog baby name will output Spot. Good stuff. A trait with an, I'm nearly certain, right? I'm a bit tired right now, so I'm just going to double check. Yep, Spot. We implement the code for naming all puppy Spot in the baby name associated function that is defined on dog. The dog type also implements the trait animal, which describes characteristics that all animals have. Baby dogs are called puppies, and that is expressed in the implementation of the animal trait on dog in the baby name function associated with the animal trait. In main, we'll call dog baby name function. We'll call the dog baby name function, which calls the associated function defined on dog directly. Code prints the following. Baby dog is called Spot. The output isn't what we wanted. We want to call the baby name function that is part of the animal trait that we implemented. Oh yeah, a baby dog is called Spot. Well, that is correct though, if all dogs are called Spot. The technique, right, so we just want to print puppy. The technique of specifying the trait name that we used in listing 1918 doesn't help here. If we change main to the code in listing 1920, we'll get a compilation error. Yeah, because we haven't put in dog, and we don't need to create a dog instance. That would be quite dumb. Huh. Attempting to call baby name function from the animal trait, but Rust doesn't know which implementation to use. Because animal baby name doesn't have a self parameter, and there could be other types that implement the animal trait. Rust can't figure out which implementation of animal baby name we want, and we'll get this compiler error. Animal baby name, defined here, cannot call associated function of a trait. Help, use the fully qualified path to the only available implementation. Dog as animal. Okay, sure. Oh, okay, so here's the syntax. That is a strange syntax, but sure. Within arrow brackets, we want dog as animal. To disambiguate and tell Rust we want to use the implementation of animal for dog, as opposed to the implementation of animals for some other type, we need to use the fully qualified syntax. Listing 1921 does exactly that. Fantastic. Listing 1921. Using fully qualified syntax to specify that we want to call the baby name function. Yep. We're providing Rust with a type annotation within a. We are providing Rust with a type annotation within the angle brackets, which indicates that we want to call the baby name function from the animal trait as implemented on dog by saying that we want to treat the dog type as an animal for this function call. This code will now print what we want. A baby dog is called a puppy. In general, fully qualified syntax is defined as follows. Type as trait for the function, and then receiver if method, or the next argument, so on and so forth. For associated functions that aren't methods, there would not be a receiver. There would only be the list of other arguments. You could use fully qualified syntax everywhere that you call function or methods. However, you're allowed to omit any part of the syntax that Rust can figure out from other information in the program. You only need to use this more verbose syntax in cases where there are multiple implementations that use the same name, and Rust needs help to identify which implementation you want to call. Using supertraits to require one trait's functionality within another trait. Sometimes you might write a trait definition that depends on another trait. For a type to implement the first trait, you want to require that type to also implement the second trait. You would do this so that your trait definition can make use of the associated items of a second trait. The trait your trait definition is relying on is called a supertrait of your trait. Trait. For example, let's say that we want to make an outline print trait with an outline print method that will print a given value formatted so that it's framed in asterisks. That is, given a point struct that implements the standard library trait display to result in x, y. When we call outline print on a point instance that has 1 for x and 3 for y, it should print the following: 1, 3 within this little box. In the implementation of outline print, we want to use the display trait's functionality. Therefore, we need to specify the outline print trait will work only for types that also implement display, and provide the functionality that outline print needs. You can do that in the trait definition by specifying outline print display. This technique is similar to adding a trait bound to this trait. Listing 1922 shows an implementation of the outline print trait. Alright, so you have trait outline print, format display. This is simply saying, hey, we have a trait called outline print, which can only be implemented on something which also separately implements format display. And then we have all of the stuff here, which just implements the box. Because we specified that outline print requires the display trait, we can use the toString function that is automatically implemented for any type that implements display. If we try to use toString without adding a colon to specify the display trait after the name trait, we get an error saying that no method named toString was found for the type self in the current scope. Let's see what happens when we try and implement outline print on a type that doesn't implement display, such as the point struct. We simply try and do this, and it says, oh no, point cannot be formatted with the default formatter. Point does not implement standard format display. Oh, the trait standard format display is not implemented for point. Note, in the format strings you may be able to use for pretty print instead. Note, required by bound inline print, required by this bound inline print, outline print. We got more error, which isn't really necessary. I guess it's just messing up in different points and showing us at every different point that it could be a problem, which is good. This is why I like Rust error handler. To fix this, we implement display on point and satisfy the constraints that outline print requires, like so. Right, we have implement format display for a point, function, format, taking a reference to self, and f, which is immutable reference to format formatter, outputting format result. And then we just say, hey, right? Pretty simple here. We pass in the formatter. We have the string, and then we take self, x, and y, placing them in these points. At this point now, we can actually implement outline print on point. We can call outline print on point. This code will work. Then implementing the outline print trait on point will compile successfully, and we can call outline print on a point instance to display it within an outline of asterisks. Right, using new type pattern to implement external traits on external types. Okay, in Chapter 10 in the Implementing a Trait on a Type section, we mentioned the orphan rule that states we're only allowed to implement a trait on a type if either the trait or the type are local to our trait. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple struct. We covered tuple structs in the Using Tuple Structs Without Name Fields to Create Different Types section of Chapter 5. The tuple struct will have one field and be a thin wrapper around the type we want to implement a trait for. Then the wrapper type is local to our trait. We can then implement the trait on the wrapper. New type is a term that originates from the Haskell programming language. There is no runtime performance penalty for using this pattern, and the wrapper type is elided at compile time. As an example, let's say that we want to implement display on vect, which the orphan rule prevents us from doing directly because the display trait and the vect trait are defined outside of our crate. We can make a wrapper struct that holds an instance of vect, and then we can implement display on wrapper and use the vect value as shown in listing 1913. Right, so we got a wrapper here, which takes in a vector string, a spectrum of strings. Then we implement format display for the wrapper, and here's the implementation here. Main function, let w equal a wrapper, taking in the string, or a vector with strings hello and world, and then we print w equals, and then this. There we go. So normally we simply would not be able to implement display on a vector, but now we can. The implementation of display uses self.0 to access the inner vect, because wrapper is a tuple struct and vect is the item at index 0 in the tuple. Then we can use functionality of the display trait on wrapper. The downside of using this technique is that wrapper is a new type, so it doesn't have the method of the value it's holding. We would have to implement all the methods of vect directly on the wrapper, such that the methods delegate to self.0, which would allow us to treat wrapper exactly like a vector. If we wanted the new type to have every method the inner type has, implementing the deref trait discussed in chapter 15 in the treating smart pointers like regular references with the deref trait section on the wrapper to return the inner type would be a solution. If we don't want the wrapper type to have all the methods of the inner type, for example, to restrict the wrapper type's behavior, we would have to implement just the method we do want manually. The new type pattern is also useful when traits are not involved. Let's switch focus and look at some advanced ways to interact with a Rust type system. Alright, I'm sorry, I am losing my voice. I've talked a lot today, and I've talked a lot during this session. That's 2 hours, an hour and a half. Hour and 43 minutes of talking on top of nearly 8 hours. Alright, so I guess this is it for today. I will do the quiz in a week. Talk to you all later, and by y'all I mean nobody today, but hey, that's okay. I'm still gonna go through this. We are so close to the end, which is kind of disappointing. This has been half a year, man, but everything has to come to an end. I say maybe 3 more sessions, and then we're done. Shame. Done before Christmas, just like the First World War. Fantastic. Anyway, goodbye, good night. Peace.